So we've learned about Taylor series, and now let's see several ways that it could help us that isn't sort of directly just expressing the function in terms of its Taylor series. And so let's see how we could work with Taylor series. One way that Taylor series could help us is in computing limits. So take a look at that limit right there. You could see that this will give us a 0 over 0. And we can use L'Hopital's rule here. On the other hand, we're taking x to 0. So why not look at the Maclaurin series of cosine x? Okay? As long as we stay close to the center, and the center here is x equals 0, then this should be a fairly good representation of the cosine function, and we could take as many terms as we'd like and get more and more accurate values for cosine x. But notice that once you're close to 0, only the first few terms will dominate. So let's do that. So we'll have we have this limit. Instead of cosine x, we're going to plug its Maclaurin series in there, and we end up we'll distribute that 2. We end up with this term here, and when we cancel, say, the x squared with that, the 2 with this, we end up with these first dominating terms plus some additional terms. And then we divide by x to the 4th, and we get this 1 over 36. We get minus x squared. And as we're taking x to 0, this is going to go to 0, and so we'll actually get 1 over 36. So that's a pretty clever way to compute limits out, where we didn't need to use L'Hopital's rule. We could do this even when we're taking limits to infinity. Okay? Now we don't do expansions at infinity. That's sort of a weird center to choose, right? We don't do that. But what could help us? Well, we could change variables. Instead of using x, we could set x equal to 1 over t, and then we know that as x goes to infinity, t goes to 0 from the right. So with this change of variables, where basically we just change wherever we see an x, we put a 1 over t, we could change the limit from x to infinity to t goes to 0 from the right, and now we are in that domain of having of looking at a Maclaurin series. Okay, taking the Taylor expansion near 0. And so we get this term over here. We could combine, we could get a common denominator, and we simplify as we see here. And now we're going to plug in the Maclaurin series for sine of t. And again, notice that the first term will dominate as t goes to 0, and we'll let the math show us that. And so we'll plug in for sine of t, we'll plug in its Maclaurin series. And we do get cancellations. Once we're done with these cancellations, we get terms that look like this. We divide by that t to the 5th, and we get that expansion there. And you're only going to get higher powers of t. And so only the 1 over 20 term will survive when t goes to 0. And so we just used the Taylor series to help us in computing limits. Well, another way that the Taylor series could help us is with differentiation. So differentiate the Maclaurin series for f of x equals sine of x to verify that the derivative of sine x equals cosine x. So there's a little bit of a strange proof without the actual series, and so maybe it's more intuitive to see the derivative being taken out on the series itself. So we have sine of x, we write out its expansion. Okay, here goes the Maclaurin series for it. It converges on the entire interval. We're going to take the derivative with respect to x of sine of x, or here it's Maclaurin series. Once we do, we get these terms over here. And that over here is the Maclaurin series for cosine x. So we just showed that the derivative of sine x is equal to cosine x using the Maclaurin series. We may also integrate using power series. So approximate the value of 0 to 1 e to the minus x squared with an error no greater than 5 to 10 to the minus 4. Again, this is sort of numerical problem. E to the minus x squared doesn't have a closed form for it, so you don't have a familiar antiderivative. Okay, so you can't just take the antiderivative and plug in the bounds. But what we can do is use the Maclaurin series and keep as many terms as we need to get an accurate value for that integral. So we have e to the x. Here's the Maclaurin series for e to the x. We want e to the minus x squared, so we use composition there with the inside function being negative x squared. And we end up with this Maclaurin series with that composition. And so the integral from 0 to 1 of e to the minus x squared is going to be the integral of these terms over here. We're going to integrate term by term. If we integrate term by term, we get this expansion here. We plug in the bound 0 to 1, and we get these terms. Okay. Now this is an alternating series, and we know from alternating series that the remainder is less than or equal to the first neglected term. And so we just test out and see that at 5, at n equals 5, we will get that the next neglected term is no greater than 5 times 10 to the minus 4. And so all we need to do, and we could test that by plugging it in, or by plugging it into over here. So here's how a sub n looks. So we could plug in 5 in here and see that that is smaller than 5 times 10 to the minus 4th, which means the remainder will be smaller than that. And so all we need to do is retain 5 terms in this alternating series, and we get this value here. And we just numerically integrated a function that we cannot use the fundamental theorem for because we don't have a familiar closed form for it. So it's not too useful. Another way Taylor series could help us is with representing real numbers. And this is sort of pretty interesting here. So use the Maclaurin series for f of x equals arctan x to evaluate this series here. That's strange, right? Well, we know, as we've done the Taylor expansion before, the Maclaurin series for arctan of x is equal to this, which we could write out this way. And now how do we make this look like that? Okay. How do we make the Maclaurin series look like that series there? Well, we would plug x equals 1. If you plug x equals 1 here, you get precisely that series. And so, okay, we plug x equals 1 in the arctan function, and we plug x equals 1 into its Maclaurin series. And when we do that, we get that this series here is equal to arctan of 1. But arctan of 1 is equal to pi over 4. So check this out. We get that pi over 4 is equal to that expansion, that series. So we have a power series representation of pi over 4. And that's one way to approximate pi, is to use that, power series like this. And so you could retain as many terms as you need to get an accurate representation of pi. And we know the remainder of an alternating series, what it is, and we could bound the error in pi as much as we want. And of course, this here would be pi over 4, but you could always multiply by 4 to get just pi. And so there goes another interesting application of Taylor series. And another application is to represent functions as power series. We've seen that. So identify the function represented by this power series. So this works kind of backwards. In the past, we've found the Taylor series for a given function. But what if let's work backwards. Let's start with a function like this. Okay, we got this power series, and we want to find what sort of function this is, okay, in terms of our familiar functions rather than just the power series. Well, we look at that k factorial, and that should give us a hint. We've done the Taylor series, the Maclaurin series for e to the x, and you know, these terms don't look too far off from these terms. In fact, if we use composition and we substitute instead of x 1 minus 2x, we will get the power series that we see above. So the power series that we see above is actually e to the 1 minus 2x, and the interval of convergence stays the same because it's infinite there. So 1 minus 2x is between minus infinity and infinity, and we'll get the interval of convergence being the real line, because all we did was compose 1 minus 2x into there. And so we could work backwards to represent power series in terms of familiar functions by paying attention to the Taylor series.